In this module, you will understand the financial operations that are embedded in Waterproof. Our countries are very interested and know that they must promote solutions based on nature, but they always face questions such as, where is the most suitable place to implement them? How do I know that my nature-based solutions project will have positive results? Would it be effective? How much does it cost me to implement it? In order to engage investment partners in the development of a nature-based solutions portfolio, it is necessary to do an ongoing cost and funding sources rather than a single assessment of the financial sustainability of the program. It is necessary to estimate the full lifecycle costing profile for your nature-based solutions investment portfolio, which projects costs on an annual basis over the project life. Such time-delineated costs are a key input to metrics such as net present value and return on investment, which address the time value of money. Therefore, it is necessary to consider implementation costs, which refers to the initial direct implementation costs at the site level, which includes categories such as site level, design, permits, materials, equipment, and labor. It includes initial tree planting. Also, maintenance costs, which seek to maintain the value of nature-based solutions investments and ensure compliance during the life cycle of the investment in the long term. This includes regular inspection, maintenance and replacement efforts, site-level monitoring, replacing signage, fencing. Maintenance costs are typically variable and recurrent, with the time interval dependent upon the intervention. Also included are opportunity costs and refer to the difference between the net benefits that landowners obtain from normal land management and those obtained from nature-based solutions investments. Normally, it is necessary to compensate landowners for foregoing the opportunity to use the land in another way. Note that such compensation may vary considerably and take the form of direct financial assistance or in-kind incentives. Transaction costs are those incurred to organize nature-based solutions investments, such as stakeholder outreach efforts, agreement definition, dispute resolution, training, and other activities. Transaction costs are variable over time, may occur in regular or irregular intervals, and are highly activity dependent. Remember, to be convincing, it must identify the benefits, know who receives them, how much they are worth, and when the return on investment can be seen. It is fundamental of a good business case. Waterproof provide a rapid return on investment calculation and early indication of a preferred portfolio of nature-based solutions for any watershed in the world using Models Invest and Rios, to provide stakeholders interested in nature-based solutions with a pre-feasibility assessment regarding nature-based solutions potential. Return on investment is a performance measure used to assess the investment or to compare the efficiency of one in relation to other. That is, through the following mathematical operation. The elements that are part of the calculation are described below. Benefits, time series estimates of benefits, expressed as metrics. Costs for nature-based solutions includes interventions costs, for example design, installation, maintenance costs, PSA payments, opportunity costs. Discount rate, time value of money. For companies, this is usually interpreted as the cost of capital. Time horizon, period of time to consider the investment program. In Waterproof, you will see that the system allows the user to enter a discount rate for the analysis, and a minimum and maximum discount rate in order to perform a simple sensitivity analysis. The system suggests discount rate values. However, users can modify them according to their situation. Continuing the idea, return on investment analysis of a package of nature-based solutions interventions is key, so that investors can objectively compare the results with respect to investing in gray infrastructure that would provide similar benefits. For example, to calculate the return on investment for a public services company that is interested in reducing the amount of sediment in the water it filters, it is essential to understand its filtering process and the costs associated with that process. If nature-based solutions interventions in the watershed improve soil retention, thereby reducing the concentration of sediment reaching the filtration plant, this may justify the use of fewer chemicals to purify the water and sustain savings compared to what they invested in the watershed. Then, the return on investment calculation in waterproof is based on the results of the simulation of the ecosystem services for business as usual scenarios, compared to the nature-based solutions implementation scenario. As a first procedure, it is necessary to approximate changes in ecosystem services over time. In the graph you can see with the red boxes the coverage changes that can be achieved with the implementation of nature-based solutions. This is achieved thanks to the use of the INVEST model because waterproof estimates the concentrations of sediment, nitrogen, and phosphorus in the water body at the water intake point. This is to estimate the water quality characteristics at the water source. Then waterproof with its algorithm generates a raster of land uses considering the effect of change in coverage expected by the implementation of the nature-based solutions. So, as you saw in the previous module, INVEST is a model that offers different calculations to determine the basin conditions in relation to annual water yield, basic flow, sediment delivery ratio, nutrient delivery ratio, phosphorus, nitrogen delivery ratio, carbon storage and sequestration. Waterproof simulate ecosystem services for a nature-based solutions land use or land cover scenario, using the INVEST models using the expected land use layer with nature-based solutions implementation, and calculates the relative difference between the scenarios. Business as usual and nature-based solutions with this equation. Then is the moment to prepare the cost information that is required to calculate return on investment. To do this, we rely on cost functions. Cost functions are mathematical expressions that allow the establishment of operation and maintenance costs for each infrastructure element, based on variables calculated by the system. The cost functions integrate the operation and maintenance costs based on the different treatment trains and consider different technologies for several of the processes. The operation and maintenance costs of a water treatment plant can be attributed to three main centers: laborin, ergi, materials and supplies for maintenance. Each of these has a different percentage of participation in each of the processes proposed. This is the case of the treatment processes that will be more expensive if there is a greater load of contaminants understood as solids and nitrogen, since it leads to higher operating and maintenance costs by presenting greater wear on the systems, greater frequency of washing, drainage, removal of sludge, cleaning of surface plants and dredging of reservoirs and ponds. This is the reason why the functions are expressed in terms of flow rates, concentration, and load of solids, nitrogen, or phosphorus. So, in waterproof the costs are based on the different treatment trains and considering different technologies for several of the processes. An example with which this can be understood is by analyzing the operating and maintenance costs for a mixed bed rapid filter that was calculated to be $15,000. It can be considered that this has an energy percentage of 30%, labor of 62%, and materials of 8%. So we could calculate the individual costs as follows. This is done by taking into account the following definitions. Energy costs can be due to control systems such as actuators, level gauges, flow meters or equipment used for cleaning the filters. Labor would correspond to the time that the operators must dedicate to the supervision and operation of the filter. Material costs corresponded to the replacement of valves or accessories that could be damaged, in addition to the budgeted costs for the replacement of the filter bed. To conclude, variables that influence the operation and maintenance costs of a treatment system are flow rate, since the size of unit operations is directly proportional to the volume of water they treat. Pollutant load, since a greater load of solids and nitrogen leads to higher operation and maintenance costs for a process. By presenting greater wear on the systems, greater frequency of washing, drainage, sludge removal, cleaning of surface plants and dredging of reservoirs and poundages. And elasticity coefficients refer to the percentage change in treatment costs for purification as a result of a 1% change in water quality. In this screen we show what a cost function looks like. There will always be the estimation of the flow rate, the amount of contaminant load, and the elasticity coefficient. Next, you will see the way in which the cost functions are defined for some processes of the treatment train. Dredging consists of removing sediments in the form of sludge that settle at the bottom of ponds and reservoirs. The costs associated with this activity correspond mainly to labor and the provision of machinery for the development of this process. This includes fuel, repairs, maintenance, among others. It must be considered how all the sediments that are retained in a year by the reservoir are eliminated. You must identify dredging costs per ton. The lateral intakes are structures that are located on one side of the stream from where the water is being captured. The lateral intakes are structures that have a grid in the side catchment window responsible for retaining large material that can affect the operation of the adduction. The operation and maintenance costs of this structure are mainly associated with the labor required for the extraction of sediment in the collection chamber. The descenders are located close to the water collection point so that, by reducing the velocity of the water, the large particles fall under their weight to the bottom of the sand trap to be removed. Removal of grit is critical to treatment, as these large particles can affect rapid mixing and flocculation processes, as well as damage internal pump components. The cost function for the descender is based on the flow of the plant, in addition to the concentrations of nitrogen and sediments present at its entrance.